Hello and welcome for another video on Physics 2. So we're going to be doing a practice problem here, and this one is about Coulombs law. So we have two tiny spherical drops, water drops with identical charges of -1 times 10 to the -16th coulombs, and they have a center-to-center separation of 1 centimeter. What is the magnitude of the electrostatic force between them? That's part A. And part B is how many excess electrons are on each drop, giving it a charge imbalance. So we're going to need a couple of things. We're going to need Coulomb's law, of course, so that we can get the electrostatic force. And all that we're actually curious about is the magnitude of the electrostatic force. So that's going to be important here. And secondly, we're going to be looking for the number of excess electrons. And this is going to be very easy to determine, as you'll see in a moment. So one thing we should note is that the two spheres have the same charge. So Q1 is equal to Q2, and they're both equal to -10 to the -16th. Now the electrostatic force from Coulomb's law is equal to K, which is a constant, times Q1 squared in this case, because it usually would be Q1 times Q2, but Q1 is equal to Q2, so it's got to be Q1 squared, divided by d squared, where d is the distance between them, times a unit vector in the direction of the force, which is this d with a vector hat over the top of it. So we know the constant k. We can determine that. We also know that d is 1 centimeter, but we should note that the constant k there has units in terms of meters rather than centimeters. So we're going to have to convert that to meters when we do this computation. So the magnitude of the force, again looking at this, pointing at this vector d, the magnitude of the force is just the part that's boxed in there, not the unit vector. So the magnitude is just going to be k times Q1 squared divided by d squared. Now we're going to need to get this constant k, and as I mentioned, we also have to be careful because d is in centimeters and we need to convert it to meters. So I'm going to do that as I have just done. It's 0.01 meters, or 10 to the -2 meters if we want to write it that way. We're going to need k here, d squared, yes, d squared is 10 to the -4th meters. And we're also going to need k, because we know obviously that q is equal to -10 to the -16th coulombs. So squaring it is going to obviously make it 10 to the -32. And it's actually going to change that negative sign to a positive because they're negative times a negative is, of course, a positive. Down in the bottom left corner here, we're going to get k, which is 8.99 times 10 to the 9th Newton meters squared per coulomb squared. And again, I'm going to just emphasize this. We've already talked about it. I'm going to emphasize this. We have the k in terms of meters, which is why we converted the d to meters. Okay, so that's the only way to make those units match up. So now we can write out all of the terms here for the magnitude of the electrostatic force. Just put in the k, which is 8.99 times 10 to the 9th. And then we can put in the q squared, as I mentioned, that's going to be 10 to the negative 32. And because that's squared, obviously, 10 to the minus 16 squared. And then we're going to divide that by 10 to the negative 4, because d squared is 10 to the negative 4. Okay, so now we can write out the whole thing here. And we get 8.99 times 10 to the negative 19 newtons. And that's what we should expect, because we have a force. So now we're going to go on to part B. So we want to know how many excess electrons there must be, because we have some amount of charge, and there has to be a certain number of electrons that are in excess to give us that charge on each drop. And the problem that we're going to run into here is we're going to have to actually round, because we don't have exact cancellation as one would hope, but you know that there has to be a specific number of electrons. Okay, so this is a very important point. And the Q is equal to N, which is the number of electrons, and this is a really unfortunate notation, but E, where E is not the special number E, but rather it is electron, the charge of the charge of an electron. So this is a really unfortunate notation, considering how often the number E actually shows up in physics. So just to make things more confusing, I suppose. And the charge of an electron, E, is given by 1.602 times 10 to the negative 19th. Coulombs, that is. So notice that N is not going to is going to be dimensionless. It's not going to have any units, which is as we would expect. So we can actually rewrite this, because we're going to be asking how many, which is the number N. That's what we really want. So we can actually rewrite this as N is equal to Q divided by E. Right, so we can rewrite it, we can rearrange that whole formula to get there. And obviously we have an excess charge of negative 10 to the minus 16th coulombs, and the charge of an electron is negative, so we have negative 10 to the minus 16th and negative 1.0602 times 10 to the negative 19th, which obviously the negatives cancel. And the coulombs cancel too in both places. So we end up with approximately 624 excess electrons. That's all that I have for this video. I hope to see you again next time.